Everybody, my name's Alexa Goss, and today I'm going to be talking about why benzene is the bomb, but not really, it's actually a very hazardous thing. But anyways, I'll be talking about experimentally determining the resonance energy of benzene through use of bomb calorimetry. So to start off, the resonance energy of benzene can be determined through this reaction of benzene and cyclohexane forming CDDT. This is an example of an isodesmic reaction, meaning that there is an equal exchange of bonds. These reactions are theoretical and allow scientists to investigate the thermodynamic properties of molecules, since the energy change in these reactions is often negligible. It is difficult to measure the heats of combustion of gases, but it is possible to measure them as liquids via bomb calorimetry. But before I get into the details of the experimental setup, let's look at the materials that we will be investigating. So CDDT, or trans-cis-159 cyclododecatriene, is a compound used in polymer production as well as an intermediate for the production of things like flavors and fragrances. Both CDDT and cyclohexane are available for use, but benzene, however, not used in this experiment due to its concerning STS. Benzene is a known carcinogen. It has the ability to cause blood disorders, neurotoxic effects, reproductive effects, and it is an irritant. So it's really fun, right? Anyways, due to these hazards, reported values for benzene's heat of combustions were used for calculation purposes. Hess's law cycle can be used to determine the resonance energy of benzene, as it represents the total heat change for chemical reactions regardless of the pathway. The summation of the enthalpies on the right give the overall enthalpy of the reaction, or the negative resonance energy of benzene. A bomb calorimeter was used to measure the heats of combustion of liquid CDDT and cyclohexane. The oxygen bomb pictured on the screen was taken apart. The basket inside was loaded with the sample and the fuse wire was attached. And then the bomb was reassembled, making sure that it was secured properly. The bomb was pressurized to 15 atm twice and also vented twice, and then it was pressurized to 30 atm. The bomb was placed into the calorimeter bucket filled with DI water and connected to the stirrer and motor pulleys. And then the thermometer was placed inside and the ignition wires were attached. This setup was safely secured and caution was taken with every step to make sure that nothing went boom in the lab. After the experiment was completed, calculations were done using these equations. So the first equation is the temperature change that is calculated using various points on the experimental curve, which I will show later. The heat transfer total energy is defined as Q total, and its components are heat capacity of the calorimeter, which is C bomb, times the change in temperature. The sample energy is found by considering the difference in the total energy and that of the ignition wire, QW, the remaining wire, QWU, and the capsule, QCapsule. The capsule was used in the case of cyclohexane for sample. The enthalpy of combustion is found by considering the heat evolved, delta U, under constant volume conditions, and the change in moles, delta N, along with the ideal gas constant R and temperature T. The Clausius-Clapeyron equation allows for use of vapor pressures to determine the enthalpy of vaporization, and this was used for CDDT. Finally, the general enthalpy of a reaction will be used with the theoretical reaction shown previously to examine the resonance energy of benzene using the computational software Cygris. The hypotheses proposed for this experiment are that the maximum temperature will be greater for CDDT than cyclohexane due to cyclohexane having a lower heat of combustion, meaning that it should produce more heat energy. The other hypothesis proposed was that the chemicals used in this experiment have different heats of vaporization, which would cause potential issues, meaning that Cygris software may provide more reasonable values as it can optimize molecular behavior. The experimental data shown on the screen for the first CDDT run is labeled with point I, which is the temperature 60 seconds after the stirrer was turned on. Point A, which is the time of firing the bomb. Point B, which is 60% of the temperature change between points A and C. Point C, which is the maximum temperature reached. And point F, which is the final temperature that occurs about 90 seconds after point C. The change in temperature was found using the equation previously described and the points on the graph. A linear trend line was fit between both points I and A and C and F, and linear regression data analysis was done to determine the equations, error values, and R-squared values on the screen. This is the table with the points for the first CDDT run. This shows the time values and the temperature values. And then here's the table for the second CDDT run. And all of the same calculations were completed and they're shown at the bottom of the screen. And then all of this was done over again for cyclohexane. So here's the graph. It has the same color coding, all of the same points as the CDDT runs. Here's the graph for the first cyclohexane run with the time and temperature values, and here is the table for the second run. It is important to note that the runs, although the calculations were done individually, the values were averaged to complete the final calculations to get the resonance energy of benzene. Here is an example calculation finding the enthalpy of combustion for CDDT using the average change in temperature over both runs and the energy equations described before. The calculated energy was converted to kilojoules per mole using the moles of CDDT from the experiment to yield a value of about negative 7,330 kilojoules per mole for the enthalpy of combustion of CDDT. This was also done for cyclohexane. And then the Clausius-Clapeyron equation was used in order to find the enthalpy of vaporization for CDDT. So the inverse temperature was plotted against the natural log of the pressure, and a linear trend line was fit to these data points, yield the equation in R-squared valued on the screen. And then further data analysis was completed to find the standard error of regression. So this equation can be rearranged to determine the enthalpy of vaporization for CDDT. The slope of the line of regression is equal to the negative enthalpy over the gas constant. This analysis yielded a value of about 47.67 kilojoules per mole for the vaporization enthalpy of CDDT. And then here are the average calculated values for CDDT and cyclohexane to yield the enthalpy of combustion shown at the bottom with delta H for both. And here's just a table to summarize all of the enthalpies that I've been talking about, because some were calculated experimentally and some are reported. So the combustion enthalpies for CDDT and cyclohexane were both calculated experimentally. The vaporization enthalpy for CDDT was calculated from the Clausius-Clapeyron equation shown before, and then the reported values are shown below. Like I talked about, the enthalpy of combustion for benzene had to be found because of hazardous it is. So the experimental resonance energy of benzene was then calculated using those enthalpies that I was just talking about via the Hess's law cycle and the summation of all of the enthalpies. So the reaction enthalpy is the negative resonance energy, and this experiment produced a value of about 54.28 kilocalories per mole as benzene's resonance energy. And then Sigris modeling software was used to model the molecules and find their theoretical heats of formation, as shown on the screen, along with these cool Sigris models. And then here is the Sigris calculation for the resonance energy of benzene. So the heats of formation were combined to yield a reaction enthalpy of about 38.86 kilocalories per mole. And just to conclude everything, let's go back to the hypotheses. So CDDT did in fact have a higher maximum temperature than cyclohexane, but not by a very large margin. And then the error from the reported value of benzene's resonance energy, which is 36 kilocalories per mole, is much larger for the experimental data than the SAGRIS software, with about a 50% error from the experimental data and only about an 8% error from SAGRIS. Talk about some limitations of this calorimetry experiment, the compounds that could possibly be tested, and the optimization. So not all compounds are compatible with bomb calorimetry, and then some we can test so hazardous, like benzene. One solution for this could be use instrumentation such as differential scanning calorimetry for compounds that aren't necessarily suitable in a bomb calorimeter. This instrumentation utilizes a sample and a reference, and it monitors the temperature difference in between to determine the heats of reactions. Future improvements to this experiment would be to complete more trials, as this always allows for more confidence in data collection, and to collect more precise measurements, such as more precision in the length of the fuse wire, which was used in the calculations, and consistency in the sample preparation of CDDT and cyclohexane, as cyclohexane was prepared in a capsule and CDDT was placed directly into the oxygen bomb basket. So I think it would be interesting to look at if we kept the sample prep consistent, if that would change any of the data. But that is all that I have for this experiment. And that is why benzene is the bomb. So thank you guys for listening, and have a great day or night or afternoon or weekend or summer. Thank you.